Hello, everyone. Again, sorry, my name is Michael Schmela. I'm the Managing Director of Taiyang News, and I would like to welcome all of you to today's webinar on Solar Getting Smart, how digitalization boosts energy efficiency in PV power plants. I would like to mention first is that I would like to thank our sponsor, Trina Tracker. Without them, this webinar would not be possible. Thanks again. And what we are trying to do today is, as you all know, digitalization is becoming increasingly important in the power sector in general. And so it is obviously then also in the solar sector. We talk on the one hand, on the solar power plant, where it's really about optimization, about monitoring, about predictive maintenance, or just a few. These are just a few examples on where digitalization actually can take a role. And then we have to look at obviously also from the grid side of things, with solar getting bigger and bigger and taking a more important role in empowering our needs. We also have to look at demand response, ancillary services, and all of these parameters we talk about, and these needs actually can be influenced, and that's also where Trina Tracker here, our sponsor, comes into play, because with the help of trackers, we can clearly influence how we feed into the grid, and thus actually also respond to the needs. We have three presentations in today's webinar. First, we will have Jan Ossenberg, Policy Advisor from Solar Power Europe, the Association of the European Solar Sector, talk about how the framework is. It's really about the laws and how that is changing actually, and hopefully unlocks opportunities, but also poses sometimes still barriers. Jan will dive into that. Then we will have Sankai, head of Smart Tracker Control Systems at Trina Tracker, who will do a deep dive into how digitalized solar tracker systems work and how they really increase reliability and also the yields of solar power plants. And finally, we will have Miguel Herrero, who's a market and insights analyst at PVCase. And this company is all about intelligent software. And he will talk about how to manage data risks in the development and engineering phases of solar PV projects. After these presentations, we have 90 minutes and we have 60 minutes today. We want to talk and discuss a little bit what we learned, and simply kind of really answer the question how digitalization can bring PV power plants to the next level.
In the next 10 minutes, I'm going to talk about three topics. One is the development of the solar market. Then, what are the next steps for data sharing to make use of to make use of the data for the solar power plants? And the last topic, cybersecurity. Starting with market development, let's go into it. So 2022 was really the exceptional year for solar worldwide. We saw annual installations grow by 45%, and really going from 165 gigawatt to 239 gigawatt annual growth. The second biggest market is the United States, where they installed 21.9 gigawatt, which is actually 6% below what they've been installing before, mostly due to the ban on imports of solar panels, which was a little bit weakened by strong growth in the residential sector. An important market to point out as well is Brazil, which installed 10.9 gigawatt, doubling the installed capacity from the year before, really with a particularly strong growth in the small scale segment below 5 megawatt. They had a phase out of net metering scheme, which started a boost a run towards these small scale installations. The third biggest market, something that's worth highlighting as well, is the Spanish market, installing 8.4 gigawatt in 2022. And here, what is particularly interesting about the Spanish case is that most of these power plants were actually outside of subsidies, financed via PPAs, but of course also a strong rooftop solar market in Spain. Now, when we look at the future, at the time from 2023 towards 2027, we expect around 15 to 20% of annual growth. Alone in 2023, we are expecting 341 gigawatt of installations now, despite, I have to really say, despite worse external conditions. So the energy crisis narrative is going down a little bit. With that, the energy prices are also coming down, which is, of course, not that favorable for the business case for rooftop for solar, and also higher inflation, which makes it difficult to finance power plants. We are expecting, in terms of cumulative installations, we are expecting to hit the 2 terawatt mark by 2025. By 2027, the market share of China, we are expecting it to decrease, going from 41% to only 34% overall market share in 2027. While we expect the Asian Pacific region, that is everything outside of China, to show the largest gain, growing from 18% to 22% market share in 2027. Now, a particular highlight is, of course, the European market, which is really on track on meeting the very strong ambition that has been set by European policymakers of hitting 750 gigawatt DC as part of the Repower EU plans. And really the strong growth is being achieved through strong policy signals by European member states and the European Union. And thanks to those, we expect that the installed capacity to double from 2023 to 2027, from 260 gigawatt to almost 600 gigawatt. Out of these installations today, rooftop solar is still the biggest market. It's taking 62% of the installations. We expect this share to come down a little bit, hitting 59% by 2027. This is to point out that this is really only a small part of the rooftop solar potential. Previous estimations showed that in Europe we can do 560 gigawatt of rooftop solar, but now we are increasingly learning that the potential could be much higher, with up to 1 terawatt of rooftop solar potential across Europe. There was also recently a German study estimating that in Germany alone, Europe's biggest country, we can do 400 gigawatt by the technical potential. So there's really a strong growth to go. Now, going a little bit deeper into the next steps into data sharing and digitalization, the topic for today's webinar. In terms of opportunities, or what are the next steps where we are going in terms of data sharing? First point is, of course, planning of power plants. There we see two stakeholders which we really have to engage with. One is the permitting authorities, there's municipalities, and the second one is the grid operators. With municipalities, we really have to make sure that we have digital portals where we can communicate really on a live basis and in very short time spans with municipalities to get permits actually quicker. On the grid connection, what we are really wanting to see is that grid operators publish the capacity that they have available on their grids. We already see some grid operators rolling this out. On the slide, you actually see a map of Italy, which points out different grid capacities in the different regions. Yellow showing that there is a lot of grid capacity available. Orange showing it's getting less, and red is really it's turning an issue. And if you are actually able to click on this map to go down to the level of substations, where you can really tell at what substation you still have capacity available. That is a good first step to know where you have available capacity. An important next step will be to communicate also with grid operators through a digital platform to make this procedure quicker. Now, moving from the planning stage more to the design and the operation and maintenance part, there are two key opportunities. One is to merge different data sets to be able to develop and improve your equipment. So on the picture below, you see data from for inverter performance, and you can really say tell when the inverter has to be replaced, and you can when you start comparing this or merging these data sets with different data sources, you can really make even better use of those, which at the moment still poses a barrier. Second point here is to start comparing power plants with each other. So you start to look at power plant A, B, and C, and then you can compare the different performances, which allows you to get some insights on what configurations work more and what work less. The third big next step is the integration of PV assets into the electricity grid. And here we have to make sure that we have the right markets available so that there is a strong incentive to actually connect the different devices to each other. On the right, you see two graphs. One is a survey by installers indicating that around 50% of installers don't only install PV anymore, they also install heat pumps or electric vehicles or home energy management systems, really showcasing that this is not a one isolated technologies, but they're coming together. Similarly, we see increasingly smart meter rollout in Europe. So we have all this data available, which now, which of course induces a lot of complexity, which we have to reduce. And that is to optimize self-consumption. So to optimize, if you have a rooftop solar system, you optimize what's actually staying behind the meter and limit what you export into the electricity grid, which requires, of course, a lot of coordination between the devices. Second important market that we have to develop is grid services. So both local flexibility markets, but also balancing services for transmission grids. Here we also have a lot of opportunities to develop additional value for PV power plants. Third big element here to unlock to better use data for solar integration is to remove barriers for market models. So I'm thinking here now about time of use tariffs, energy sharing, but also time-dependent injection compensation when you inject into the electricity grid. These are all really incentives that allow the product developers that force grid operators to make better use of the data by integrating the assets into the time-dependent tariffs. Now, we have one important law that is coming up here, and that is the EU Data Act. The EU Data Act is now already in national transposition. It was agreed upon in June, and this law will really facilitate data sharing. Why is that? Because it requires the data holder to make data available upon the request of the user. So you can imagine you are a project developer, you have an inverter, and then you can request from the inverter company to give you the data or to forward the data to a third party, which is, for example, an O&M platform, so they can use the data from the inverter. It's a big step. For sharing data with users, there's no compensation involved, but for sharing data with third parties, there has to be a compensation. The data must be shared at the same quality as it is available to the data holder. It must be shared in a commonly used machine-readable format, including all the context information that is necessary to interpret the data. It has to be shared where feasible, continuously and in real time. So really, we see a comprehensive approach to facilitate data sharing. There are some exemptions, of course, based on trade secrets, allowing companies to develop and to develop their products and to monetize their products and maintain that advantage based on intellectual property. There are exemptions for cybersecurity reasons, physical safety, but also there are exemptions in place if the data recipient has insufficient security controls, because of course, if the manufacturer is required to share the data, you cannot leak the data at the data recipient. This is a big step towards making data available. Now, how this will be implemented is still to be seen. The text is quite broad. It lacks details. There are no precedents for this text. So in the end, it will really depend on national implementation on how this will turn out. There is a risk that this will be fragmented across European market. And as there are no precedents, there could be the EU Court of Justice, which in the end speaks or changes the implementation across European member states. Now, for us as the solar sector, we now really have to define what this means for electricity undertakings. We have to define the exemptions for this data sharing. We have to define guidelines for remuneration for data sharing. And of course, we also have to define the modalities of how we want this data to be shared. So the roles, the rights, the responsibilities, any standards that are being used, communication protocols. So really the technical details. Now it is for us to show the European Commission how we can transpose this Data Act for the electricity sector. Coming to the last point of this presentation, cybersecurity. Now, with all this energy data being available, we are, of course, increasingly exposed to cyber risks as well. That is risks of losing data, risk of data being manipulated, which can contain privacy-relevant data, and which in the end can turn to litigation claims for the manufacturers. That is the first risk. There's also a risk of temporary failures of power plants. We consider this to be less of an issue in general, because inverter manufacturers can usually reboot the device, which can then bring the power back on. As well as if you lose a solar plant for 1 hour, the damage is relatively limited. The bigger risks that we see is if in the future terrorists can actually target blackouts by manipulating the PV data. And this is especially relevant when equipment is targeted at the fleet level, and especially if vulnerabilities can actually not be removed quickly enough. You can either cause the grid to collapse, which takes time to start the grid again, but you can also cause physical damage to the devices, which then in the end will take even longer to reboot. Vulnerabilities, the most common vulnerabilities here are remote control capabilities, insecure system configuration, which are really at the forefront. We have a lot of attack surfaces, starting only from outdated software, weak authentication mechanisms, configuration errors. The list is quite long here. And what we see is that the high-quality manufacturers take a lot of measures to mitigate these risks, but with low-cost products, we are more concerned when they have actually insufficient cybersecurity protection. Now, also here, the EU is taking some steps. There are two legislative proposals out there. There's the NIS2 directive and the Cyber Resilience Act, where the NIS2 creates horizontal requirements for network and information systems, especially for entities in critical and important sectors, which have to take cybersecurity measures and which can be controlled by state authorities. So this is for network and information systems. Now, the Cyber Resilience Act really focuses on the product level. And on the graph on the right, you see what obligations are becoming relevant for manufacturers. So it really starts with the design phase, where the manufacturers have to do an assessment of cybersecurity risks. Then in the design phase, they'll have to consider any vulnerability that they have discovered in the assessment, consider this in their development process. They have to plan vulnerability handling procedures, and there are really far-ranging reporting obligations which require a manufacturer that has been subject to a cyber attack to report this to government authorities. All these procedures taken by manufacturers are being controlled by state authorities for products that are less risky to harm public infrastructure. A manufacturer can fulfill the requirement by adopting a certain standard or by complying with a certain standard. But for devices which are actually with critical impact on the infrastructure, there is a third-party assessment necessary, where state authorities really control how manufacturers have implemented these measures. And again, this also is a broad text. So now we as the electricity sector, as the solar industry, have to now go into detail to make sure to show what does this actually mean for the different products in the solar value chain and how we can implement this and make this work in practice. These are the next steps for us. This has been it for my presentation. The last thing that I want to share with you is invite you to join us in Solar Power Europe's digitalization workstream. We have been developing all these ideas in this workstream. Please join this discussion. Thank you very much.
Thank you very much, Taiyang and Trina Tracker, for the invitation to speak today. My name is, as mentioned by Michael, Miguel Herrero, and I work for PV Case. Now, before diving into the thick of the topic of this very long presentation title, I wanted to give two quick pieces of additional context. The first one is that in addition to building a lot more solar every year, we are also experiencing a trend of solar PV projects, really utility scale PV projects, really growing massively in scale, and actually across all regions, Europe, USA, and the rest of the world, we have seen a doubling of the average sizes of PV projects since 2015. And in fact, in the USA and outside of Europe, PV projects are on average twice the size as in Europe. And this is already a challenge, but we're also adding two very important layers of technological complexity, because on the one side we can see year-on-year increases in the use of trackers, and particularly a growing trend towards smart trackers and trackers that utilize backtracking algorithms. And thanks to the achievement of cost parity between bifacial and monofacial modules, we're seeing a very steady increase of bifacial module use. And according to the AITR-PV, we can expect that by 2027, more than half of all modules used globally will be bifacial. Now, this brings a big challenge that we call data risk, which is basically caused by these technology trends, this increased complexity of PV projects, but also compounded by the chronic scarcity of skilled workers that we're all feeling. And in the case of the products that we develop, particularly qualified designers and engineers. So while we have these two trends, we can also see that the PV industry has to execute more and more projects in an increasingly competitive environment, delivering all of these increasing number of projects at a lower cost and with shorter timelines. What this has created is a huge demand for products, for software tools like the ones we develop, but which help automate and improve a lot of different steps within the project development, construction, operation, and maintenance. Now, the key issue is that a lot of these software tools have been developed, focused on very specific project development steps. A lot of these softwares don't necessarily always use coordinated data format and structures. And more often than not, unfortunately, they rely on static file formats, specifically PDFs, as a way to transfer information. Now, as a result, what happens is that information and data about PV projects gets lost throughout the PV project development process, which basically looks like this. If you were wondering, I might not be surprising a lot of the project developers out there, but it's pretty striking how complex all of these lines show different moments, different stakeholders across the PV lifecycle are requesting or sending information about a same PV project. And across all of these little lines, there is an ever-growing data risk that data will get lost at further stages. Now, PV Case is software development company. We come from Lithuania, and what we do is we develop software to design, analyze, and optimize solar PV assets globally. We have 4 main products: PV Case ground mount, the AutoCAD plugin that everyone already knows and loves, PV Case roof mount AutoCAD plugin that we are currently launching to design CNI rooftops. Anderson optimization, site selection automation tool to help with all of the GIS analysis and needs for project developers, and PV Case yield, a next generation yield analysis tool. What we do basically is we develop these tools that deliver mission critical software for our clients, and making sure that all of these are category leading products, which help drive design standards and improve these design standards in our clients, and crucially, increasing process efficiency for all the people involved in actually having to deliver all of these increasing in number and increasingly complex PV projects. Now, in about 5 years, we've grown to be a global company. There's more than 1 terawatt worth of projects, of individual projects being designed in our tools every single quarter. We have more than 1,000 customers, 1,200 customers globally across 70 countries, and with colleagues in over 20 locations around the world. Now, how are we doing? What are we doing to address data risk? One of the key areas that we are quickly identified where we could have an impact is in the site selection to project design stages of the development. Now, traditional greenfielding of PV projects basically requires to first have a GIS team, sometimes in-house, sometimes third-party, that takes care and upkeeps a GIS server with all of the needed data to develop a project. On the other side, you have a development team, which is looking for the best sites to build projects and who is drawing criteria of what that project needs to go ahead. The problem is that traditionally, the development team cannot really access the GIS server because it's very complex and it's upkeep by the GIS team. So what they have to do when they want to find out where to build a project is they basically send an email or give a call or an SMS to the GIS team that responds to them with the information that they need to build the project. Now, as you can imagine, this is not a very efficient system. You need to draft your email, wait for your GIS colleagues to respond, and then if there's a problem or maybe you want some more information, that process needs to happen again and again. What we want to do is basically automate this process by adding a layer, a software layer, with Anderson Optimization's Prospect platform, which basically helps the development team quickly and intuitively access the data they need in the GIS server to identify the best sites and analyze them in order to develop the projects, leaving also the GIS team unbothered to actually do what they do best, which is to make sure that the data in the GIS server is as reliable and trustworthy as possible. Now, the way we're doing this is very simple. We are adding a button in PV, or we have added a button in PV Case ground mount, which enables our users to directly import the site GIS data into AutoCAD, reducing all of this back and forth so that every piece of data within Anderson Optimization Prospect is imported into ground mount. This includes hazards, offsets, and whatever other GIS terrain data you have access to, so that it is immediately included into your design platform, so you can get on with defining the best layout you can for your project. Now, another area we are really working hard on reducing data risk issues is a conceptual design phase. Now, this is basically the moment when project developers are looking for the best configuration for their project, which provides the biggest financial revenue and obviously secures project funding from investors or otherwise. Currently, concept design workflows rely again on manual data exchanges between two or more separate software platforms, which notably go through 2D models. Now, this not only reduces simulation accuracy and obviously, the aforementioned issues with manual communication, but it also reduces a lot of the information contained within the 3D model that you can create in PVK's ground mount. The fact that it's a 2D model also means you have important limitations to simulate hilly terrain, trackers, and bifacial modules. And ultimately, the fact that it's a manual process is an issue because concept design relies on creating multiple iterations on the same design to find out which one is the best, and it's incrementally improving iterations. So what we are doing right now, and what we've actually already done, is with our yield simulation tool, which relies on 3D ray tracing to simulate the 3D environment of the PV plant. We are completely integrating the design phase and the simulation phase, helping our user design whatever project they can think of in PVK's ground mount. And basically, because 3D ray tracing fully takes into account the 3D design, we can easily simulate difficult topography, trackers, and bifacial modules, and how these impact project performance. But maybe going back to the data risk topic, what we launched only a few months ago is a iteration engine, which allows users to export multiple designs scenarios into yields simultaneously, where they can all be calculated concurrently. What you're seeing on your screen is how it works. Iterations are done by both tilt and pitch for fixed tilt systems, whereas trackers only allow for pitch. All of these iterations are generated on PVK's ground mount to understand how the layout might change, and then you can automatically find all of these iterations and different scenarios in your yield platform to analyze in detail where the losses might be. Another area where we are very excited about, and I think this is particularly relevant following Kai's presentation and something we're focusing a lot of R&D efforts, is to simulate projects that use terrain-aware backtracking system. Which, as Kai explained, is a very growing trend, which has very, very significant promise to unlock yield increases in utility scale PV plant. Now, currently simulating these can be quite challenging because the standard way to use 2D view factor to simulate them, but because terrain-aware backtracking target a 3D problem, namely inter-row shading between frames at different angles, you really, really need a 3D solution. And I think Kai's 3D engine really goes and shows how that worked very well. So what you can see on your screen is how our 3D backtracking works in the morning and afternoon hours, and how we are really simulating and optimizing the angle of all of the trackers in our virtual plant to increase generation of the plant. And this is something that we can already that we're working very hard to be able to bring to all of you very shortly. Overall, I think we're really with these three product integrations, we really aim to ensure that data sets and project information is easily and fully transferred between tools and across project lifecycle stages to ensure that project quality can be at the highest level for our customers. Now, a quick word on the way forward. I think we're really excited about the potential for digital twins to create single sources of truth for PV projects. Now, we are part of the very amazing, which I think was also mentioned before by Jan, Horizon 2020 Trust PV project, and led the development of two frameworks, one for conceptual framework for digital twins in the PV sector, and also for building information and modeling. Won't go into the details, but what you see on the right is basically how this looks graphically. Digital twins rely on geospatial context and geometry, functional connectivity of all of the components of the plant. Obviously, the component properties have the ability to track changes happening on the plant and are ideally based on standard and open formats. And these apply for all of the stages of the PV project lifecycle, from conceptual design all the way to decommissioning. What we see right now is that PV case is very present in the initial parts when PV projects are digital models. But what we see is a huge potential to make sure that the information that is created in the initial stages of the project lifecycle live on as digital twins by working with all of the magnificent companies that you see on screen. And again, make sure that there is no data risk across the project lifecycle. So in two words, what we think is that digital twins will definitely be an important way to make sure that the information is not only not lost, but reused across the project lifecycle. And this is our long-term vision, this has a huge potential to increase process efficiencies, minimize data risk, and basically help us all in the PV industry be able to deliver all of these projects and more complex projects to the highest quality standards. Now that will be all from me. Here are my contact details. Make sure to scan the QR code if you would like to learn more and to have a look at all of these different products. I will be very happy to take on your questions.
Hello, everyone. I'm Kai from TwinTracker. I'm so glad to be here to talk about digital implementations in solar trackers. Today, I'm going to share with you the digital application in solar trackers. This technology is driving a significant advancement in the PV industry. Okay. My presentation will include digitalization of solar trackers, Trina Smart Tracking Solution, Trina Smart Control System, and its outlook. These areas represent Trina Tracker's innovation and the boundless potential of solar energy in the future. First, let's begin with digitalization of solar power plant. PV technology has been a crucial clean energy solution. Digitalization and intelligent technologies are now the key to unlocking the future of solar energy. They provide comprehensive monitoring, maintenance, optimization, and management tools, enabling solar tracking systems to generate electricity more efficiently and collaborate with smart grids. This digitalized and intelligent technology drives the PV industry towards achieving carbon neutrality goals, providing a powerful impetus for sustainable development. Next, let's explore how digital technology is transforming our perception of solar tracking systems and shaping our future energy landscape. In this field of solar tracker-based PV stations, digital and intelligent technologies are extensively applied throughout the entire life cycle, enabling the creation of a truly smart energy source. This process can be summarized in 4 key stages. The first stage is design. At this stage, engineering methods such as finite element simulation are employed to simulate and analyze the structure. CAD software is used to create precise design blueprints. Structural analysis software assesses the strengths of the solar trackers. 3D modeling and rendering is utilized to create 3-dimensional tracker structure models with visual effects. Precise algorithm models are employed to optimize system performance. PV power generation simulation software is used to simulate and predict the electricity generation of the PV system. These measures ensure the precision and the efficiency of the system design. The second stage is construction and installation. Utilizing building information modeling for digital architectural design and management to coordinate and optimize the construction process. Employing drones for visual inspection, monitoring, and surveying, leveraging smart devices and machinery to enhance construction and efficiency through automation and smart technologies. Conducting laser scanning for precise management and modeling. Implementing digital planning and coordination to ensure adherence to construction schedules. Utilizing mobile applications for on-site management and communication, along with automated construction methods to enhance construction quality and efficiency. The next stage is commissioning. During commissioning stage, the use of digital monitoring platforms coupled with remote diagnostic tools is employed to identify and resolve potential issues. Last but not least is operation and maintenance stage. Real-time monitoring and control are possible, allowing for immediate system adjustments. The operational status is visualized, enabling operators to intuitively understand the system's coordination condition. Real-time monitoring of electricity generation data, including the recording and analysis of actual electricity generation, is conducted. IV curve and performance analysis tools are employed for the rapid identification and the resolution of issues, accompanied by real-time fault alerts and fault localization analysis. Through equipment availability statistics, diagnostics, and root cause analysis, equipment failures are predicted and properly addressed. To summarize, these technologies enable PV power plants to achieve electricity generation, enhanced safety, smart monitoring, and intelligent maintenance, paving the way for a sustainable future in renewable energy. However, traditional tracking systems currently face several issues. For instance, under overcast or rainy weather conditions, these tracking systems continue to operate at conventional tracking angles, failing to fully capture solar diffused irradiance, resulting in energy waste and inefficient operation. In uneven terrain, modules located in low-lying areas are shaded by front row modules, leading to a reduction in power generation. Additionally, in the case of a malfunction in the wind speed sensor, the tracking system, in its commitment to ensuring the tracker safety, will keep the trackers in a specific safe position until the sensor is repaired or replaced. During this period of time, the trackers which should have followed the sun's movement, remain fixed tilt in a particular position, leading to a power loss. Furthermore, the tracker's control system offers multiple power supply options. For tracking systems equipped with lithium batteries, during continuous rainy days, the tracking system may enter a low battery mode. Two issues arise. Firstly, adjustments to other operating modes cannot be made in this state. Secondly, when the weather returns to clear skies, it requires some time to recharge before returning to normal tracking mode, resulting in a certain amount of power generation loss. To address this issue, TwinTracker has developed a smart tracking solution with a focus on high reliability, high performance, and high efficiency. The smart tracking solution is comprised with various series of trackers and a smart control system. They are Vanguard 1P, which is designed for vertical single row and offers a slope adaptability of up to 20% in the north-south direction. The tracking range is 6 degrees with a 20% increase in operational wind speed. It is also compatible with cleaning robot solutions, making maintenance more convenient. Vanguard 2P designed for vertical single row and features a multi-drive design for increased stability and reliability. It can support the installation of up to 120 modules with a slope adaptability of up to 15% in the north-south direction and offers low maintenance costs. With 7 support columns per set and 102 columns per megawatt, it reduces construction expense and is well suited for complex terrains and challenging environments. In addition, TwinTracker also offers Agile 1P, a dual-row linked tracker with vertical installation of modules in one row, and fixed origin, a kind of fixed tilt supporting structures. Besides these supporting structures, TwinTracker attaches great importance to the digital technology-based software inference in the whole solution. Hence, smart control system is offered. Next, I will introduce the 3 products in Trina Smart Control System. First, let's take a close look at the track controllers. TwinTracker offers multiple stable wireless communication methods to fulfill various requirements in different regions. TwinTracker implements multi-level wind protection, snow protection, and hail protection to enhance system stability, ensuring reliable operation even in extreme conditions. Additionally, TwinTracker utilizes dual power supply solution to reduce the usage of battery and extend the battery's life, and further mitigate the risk caused by battery fault. TwinTracker offers various power supply options to meet different requirements, including stream-powered, self-powered, and AC-powered. Furthermore, TwinTracker's smart controllers also integrate with state-of-the-art smart tracking algorithm SuperTrack, providing advanced tracking capabilities for different scenarios. The next product I will share is Trina Smart Cloud, a track-level SCADA. This digital software platform allows for real-time monitoring and recording of track operational data, dynamically displaying equipment status. It can also transmit operational data to the plant-level SCADA. The data supports fault analysis and daily maintenance effectively, enhancing operational efficiency. In the coming year, TwinTracker will introduce the next generation Trina Smart Cloud, which is featured with 3D digital map, motor diagnosis, and pre-warning, and other digital tools to provide intelligent and precise maintenance. TrinaTrack will also enhance system reliability through multi-role permission management, Active Directory account management, master-slave redundancy design, and data sharing. These additions will further ensure system stability and safety. Here is a trailer, and let's have a first look of the 3D digital map. Trina Smart Cloud will simulate the 3D layout based on the actual arrangements of the trackers. This simulation achieves an accurate representation of the real tracker layout and status. If a particular tracker is displayed in gray or yellow, it signifies this tracker is in an abnormal state and requires maintenance. This visual representation will provide the most intuitive form of presenting track information, ultimately enhancing maintenance efficiency. SuperTrack is a highly intelligent tracking technology designed to boost the power generation and reduce power loss due to rotary shading. And it is adaptable to various complex terrains and comprises two core algorithms. The first is Smart Tracking Algorithm, STA, which leverages the patented bifacial irradiance model of Trina and improves the generating power on a cloudy day or in other conditions with highly diffused irradiance. The other is Smart Backtracking Algorithm, SBA, which utilizes operational data for disturbance training, or in some cases use the terrain data to identify potential shading and then reduce generation loss due to rotary shading, which are more significant on complex terrains. SuperTrack integrates diverse data such as meteorological, power generation, terrain, etc., to fully explore optimization possibilities in different scenarios. SuperTrack operates efficiently and reliably through a combination of key mechanisms. Next, let's delve into SuperTrack's operational logic. The Smart Tracking Algorithm, STA, uses real-time weather information and historical meteorological data. On cloudy or overcast days, STA adapts to appropriate tracking mode to fully capture diffuse irradiance. As for how to cope with complex terrains, SuperTrack provides two optimization methods. First, when it acquires terrain slope data or identifies terrain through drones, it generates a 3D representation of the landscape. Using this 3D terrain model, SuperTrack iteratively makes decisions to output the optimal group of backtrack angles to maximize overall energy generation. The second optimization method involves intelligent integrating PV stream data. SuperTrack leverages real-time generation data, identifies the tracker's shading status, and then sends a series of training commands to trackers. After training and based on the feedback data, SuperTrack will analyze and determine the optimal tracking angles. Finally, let's conclude with a brief summary and have an outlook of Trina's smart control system. Trina's smart control system is comprised with three parts, and they are track controllers, smart tracking algorithm, SuperTrack, and track level SCADA, Smart Cloud. Trina controllers will focus on the current pain point issues in this industry and ensures stable communication, reliable power supply, and high-quality battery performance. TrinaTracker will continuously enhance system robustness to meet diverse customer demands. On basis of what's being offered, SuperTrack will focus on the research on more sophisticated algorithms in more complex scenarios, such as north-south slope inference, seasonal variations. In short, SuperTrack will be much smarter. Smart Cloud will further improve the system reliability and develop more advanced functions, such as health diagnosis, 3D digital map, etc., to further enhance O&M efficiency. Okay, so that's all for my presentation, and thank you all for your time. I would be glad to have more communication opportunities after this webinar. This is my LinkedIn, and it will be my main social media. I will post and share my views there. Next, I will play a short video that shows my commissioning colleague Ross' comments on smart track control system. Please enjoy.
I'm Raul, TrinaTracker's commissioning team, and my experience with the smart tracking control system has been highly favourable. In the initial phases of project deployment, the seamless integration of Trina Smart Cloud into the network setup stood out. To access operational data from the tracking system, all that's needed is to connect the computer to the network using an Ethernet cable. Through this platform, we can effortlessly gather information about the tracker's operational status using a common communication Modbus TCP protocol. The digital control system, Trina Smart Cloud, shows the real-time status of the trackers through color codes, providing alarms and maintenance recommendations directly on the computer screen. This functionality allows for efficient and prompt troubleshooting of any issues. When I need to inspect a specific tracker, I navigate to the TCU interface, selecting the tracker details data. Trina Smart Cloud includes real-time status, tracking angles, and warning messages. These user-friendly interfaces will prove beneficial for our customers during operation and maintenance activities. Trina Smart Cloud has significantly enhanced our after-sales services, enabling us to promptly address customer requests. 2 weeks after the power plant commenced operations, a customer reported a recurring communication alarm in one tracker. Initially perceived as an isolated incident, the issue persisted for 2 weeks without resolution. With the customer's approval, I remotely connected to Trina Smart Cloud and examined the tracker data. It became apparent that the alarm only occurred during morning and evening periods. Upon analysis, we identified a fault in the wireless communication antenna as the root cause. Operational instructions were swiftly provided, and thanks to the responsiveness of Smart Cloud, the entire process took just 2 hours, ensuring a rapid response to the customer. Without Trina Smart Cloud, I would have had to undertake a 4-hour trip for on-site troubleshooting. However, Smart Cloud allowed me to deliver a remote solution, significantly reducing both time and cost. After monitoring the performance of SuperTrack for the first 6 months, there has been a significant increase in electricity generation. Why? SuperTrack maximizes the utilization of the diffuse radiance. For instance, even on a standard cloudy day, it enhances the daily power output of the plant approximately by 5%. Additionally, SuperTrack reduces shading losses due to terrain slopes, increasing power output during the backtracking period. This estimation indicates that the power generated by this plant is expected to meet the electricity needs of approximately 8,000 households. TrinaTracker plays a crucial role in making this achievement possible.
Brief panel with the 3 presenters. So we've seen a lot happening on the digitalization side of things. So, but if we look at theoretically what's possible in terms of digitalization today, let's maybe say 2025, because I think a lot is happening also in this project, PV Trust, as you've seen, Miguel, and what's actually being implemented. If you look at the range from 1 or scale from 1 to 10, where would the industry be in a year from now? So from actually utilizing the potential of digitalization, and I'm talking now about the solar industry, not necessarily the grid people, the DSOs, and so on.
Sorry, Michael, is this a question to
to all of you? So everyone,
okay.
Maybe you start actually, and then we go to Kai and then to Jan.
I guess I jumped too quickly at that. I mean, I think we're really at the beginning of the process. It's quite striking to a lot of my colleagues that don't come from the solar sector when they realize the type of tools, the type of processes that we have. You know, they come from industrial manufacturing or automotive manufacturing, and they see the digital tools that are still being used in the PV sector, and it's still quite. They actually tell us we're maybe 10 or 20 years behind. So there's so much we can do to improve, and I think that's just super exciting because with all of the challenges that we have, I really think that there's that digital solutions will definitely help us overcome them.
And even if we are at the start of the evolution, would you think that at least the industry is really embracing what we have, or do you see a lot of hesitance?
In the stages, project development stages, I know best, which are the development, the conceptual, preliminary design. I think, yes, it's being embraced full on. We really see a huge appetite for more, and a lot of enthusiasm because people really feel it in their day-to-day lives, how much time, sweat, tears, and money they are saving thanks to the efficiency that we provide them.
Okay. Kai, so what's when you look at that from the tracker side of things, a lot has happened also, and there were a lot of challenges also with trackers. There were bigger modules and all these changes that happened. So a lot of challenges. So how is digitalization actually being embraced here?
Okay, so actually, during my presentation, I have actually roughly demonstrates. Actually, digitalization has been everywhere in tracker-based PV industry, because as I showed in the 4 stages, right, from design to the final O&M. So actually, digitalization has been everywhere. Actually, right now I agree with Miguel, because right now I think it's still probably it's on the very early stage. We have a lot of work to do. For example, and speaking of digitalization, most people will talk about the digital platform. I mean, the track level SCADA or the plant level SCADA. Actually, now I think the functions is not so comprehensive. We can do more analysis based on this platform. We can use these functions to improve the O&M efficiency, because right now a lot of clients for trackers or for the PV plants, they say, okay, so it's still very challenging. It's difficult to do the O&M work. So can you give us more, can you provide more or better solutions for O&M? Actually, I think digitalization can help a lot. As I stated, right now for tuning tracker, we are planning to do more on this aspect. For example, next year we'll officially launch the 3D digital map, as I showed a little bit, because that would greatly help the O&M staff to do O&M work. And on the other side, for example, right now, because PV is actually is a kind of investment, right? We need to increase the energy yield and to lower the LCOE. And I think digitalization based technology such as SuperTrack, because SuperTrack right now on one hand it uses physical models, the PV models. On the other hand, we also use the big data. We use big data to do the sophisticated algorithm to to better, move the trackers to capture more, effective light to boost the energy. So to further improve the PV system reliability, efficiency, and performance, I think we must rely on digitalization. Yeah.
Okay. Jan, you in your last slide you also showed the digitalization workstream at Solar Power Europe. So I think Solar Power Europe is working a lot on this topic, and you're bringing together a lot of different views. The developers, actually their O&M companies, but also distribution grid operators. So I think there's and even so that means so how do you see actually the industry in this on this evolutionary scale, and how quickly are things moving?
Yeah, I must say I agree with Miguel and Tsunkai that we are really only at the beginning. So on the project operation maintenance, project design topics, Miguel really pointed out the most important elements. On the grid integration things, we are also in very early stages. So, but the problem here is that we really don't have enough incentives for companies to really develop these solutions. So there are no flexibility markets available, which of course means that any types of development of digital solutions, communication with grid operators providing ancillary services is lacking behind, because there's no reason for the companies really to develop these services. And the same applies for self-consumption optimization behind the meter. Actually, what we see is only heat pumps, solar plants, EV charging systems that come from one single installers are actually optimized for each other. But the ones that come from different installers, they just work separately from each other. There's no interaction happening. So really here we are also in the early stages. And the same applies to planning of power plants, both large-scale utility-scale power plants and small-scale power plants, where really grid operators and municipalities are lagging behind. Here, it's not part of the solar industry. The solar industry would love to push this more. This would make their lives so much easier. But it's actually these municipalities who don't have the sufficient staff. They don't have the staff to develop a digital platform that would facilitate all of this. Then on the grid operator side, you have more than 2,000 grid operators in Europe. Of course, we have some that are quite advanced. We have ones that really have great platforms available out there. We also have member states like Germany, which actually require grid operators to roll out such a platform, which is great. But the majority of these grid operators, again, they don't have the staff, they don't have the skills to develop this, so they are lagging behind. And here we really need legislation to bring this forward, because in my opinion, they're not going to move by themselves.
But how quickly is this happening? Because I think the challenges are apparent, right? So I think it doesn't matter if you're on the distribution grid or the transmission grid. I think there's everywhere bottlenecks. We see more and more curtailment. We see actually all these problems that were there. We see, of course, a little bit more hybrid system now coming online, where people combine solar with wind, with storage, actually to get and actually even share grid connection points to simply be more efficient. But policymakers see that, because there are targets for renewables, there are targets for solar and wind, and we have to get that going. And digitalization is key. So if you look into, I think 5 years from now, so where would you see us? You're in Brussels. You see actually how things are moving, both on the Brussels level, on the European level, but also on the national level. So,
yeah. So unfortunately, I must say that 5 years we will be able to see the first steps, but not necessarily more than that, because there's more to do than just the digitalization of the assets. Policymakers, they see the problems that you've just pointed out, but the problem is it doesn't translate into a need for action as grid operators, as in we have to digitalize. Grid operators, they are incentivized by the remuneration that they receive, which is a regulated thing. They are remunerated for the static electricity grids that they put on the ground or under the ground, and not for developing a digital solution. So here we actually have to change the remuneration schemes for the grid operators to really give them the incentive to roll this out. That is really key. And if the EU starts doing this, it takes them 1 or 2 years to develop this, to think this through, really what is the smartest approach. Then you have to calculate another 1 or 2 years for national implementation. And then we are already at 3 to 4 years. So we really have to, in 5 years, we will see probably good steps. We will see like a lot of initiative. But for the full deployment of these solutions, we might have to wait maybe 7 or 8 years.
Okay, maybe Miguel, just on Spain. So because I think that's one of the biggest markets in Europe. Last year it was the biggest market in Europe, and it's also the biggest market for ground mount systems, obviously. So, but there's a lot of talk about cannibalization, and of course, grid connection is also a problem. So how do you see digitalization, especially in Spain? Because of course it's such a sunny country, and I think so solar can play such a big role. The pipeline of developers is huge. They really would like to build more. So how is the government, maybe old new government, actually looking at these things?
Yeah, I mean, I think Spain is always an interesting country for solar because of its huge solar potential, but also because it is sometimes too ambitious even for itself. So I think, right now the whole situation in Spain with grid access is very problematic. I didn't get into it, but one of the so Anderson Optimization Prospect, we are currently launching it in Spain, Germany, and in the UK. And it's sometimes very difficult to even access the GIS data that is required for Anderson Optimization to run. We eventually got it. Spain is actually not the worst in Europe, but for me the key challenge right now in Spain, and I think this applies everywhere else, and Jan alluded it earlier in his presentation, is really on the distribution system data. Many times distribution system capacity, unlike in the map that Jan showed, is not available. Simply, it does not exist, neither in digital nor in non-digital formats. And I think really if we need to think as a sector, not as a PV sector, but as an electricity or an energy sector, on how we are going to work together, because I'm not sure we have the time to wait for policymakers to push for policy solutions to problems that are actually between two industrial sectors of the same industry, namely electricity transmission and PV projects.
Okay, maybe final question. So to Kai, I think you're building trackers around the world, and they can, as you also showed in your presentation, take an important role when it comes to flexibility. Yeah, so because I think you can really kind of basically steer the system according to the needs of the system. So when you look at the different markets, where can you actually see some positive developments regarding flexibility and digitalization?
Okay. Yeah. So here, first I want to confirm. So the flexibility from your question refers to the flexible movement of the trackers. This is the tracker feature. So what do you mean by saying flexibility? I need to figure it out.
No, I mean, of course, the flexibility that the system can bring by actually adapting it to the course of the sun, as you've shown, actually. So where are you seeing actually that solar power plants using trackers are implemented in an intelligent way so that their capabilities are really also utilized.
Mm-hmm. Based on my experience, so I think it's quite different in different regions. For example, in mature markets such as US, in EU, in Latin America. So almost for these regions, and I mean trackers, single axis trackers is almost like a standard. For example, if a developer wants to develop a project, a PV project, and they would choose track by default, but it's quite different in the developing regions such as in China. For example, right now people still are observing and they are evaluating and calculating, and because they don't have much experience of using trackers, so they are waiting. So in these regions, for example, trackers is used or not is a question. So not to mention to digitalization. So my experience tells me that in mature markets such as in EU, in Latin America, when people choose trackers, usually they have would choose like optional service such as they will purchase like the digital platform to better support them for O&M. They will choose like the smart tracking algorithm. Though it's they will pay extra money, but they still want to have these value added products because they have seen the potential values of these products. And for the smart tracking algorithm, for the digital platform, they are all closely related with digital technologies. So I mean, it depends. It varies with regions. So right now, we will adopt different promoting strategies in different regions, and especially in the developing regions, we are promoting digital technology related products. We that's what we are doing. But in mature markets, most of the time we are specify the difference between trainer products and other products, and that's what we do. So I think it is quite different in different regions.
Okay, maybe a final question to each of you. So if you think about digitalization, so what's the most important digitalization in the solar sector? So what's the most important thing that needs to be done from your perspective to bring it to the next level? You want to start?
I mean, I guess it's easy to buy more PV case licenses and products would help. No, but more seriously, I think what really needs to happen is what we were talking about last year or this year in the Solar Quality Summit. We need to really move towards a quality mindset. We need to make sure that all of these projects that we're building are going to be operating at the best possible way in 30, 40, 50 years.
Okay, super. Jan?
From my perspective, of course, regulation, I wouldn't be here if it wasn't for regulation, but key really is to have incentives for manufacturers, for project developers to use data. That is really key. If there are no markets for flexibility, if there's no clear use case to use solar assets flexibly, then why should someone develop this? So there has to be a strong market pull.
Okay. Kai?
Okay, so my view is because PV is investment, we must ensure that the investors can make money. So we need to try our best to increase the PV yield, and based on track-based PV system, we first need to make the system is reliable, is stable. So, the digital platform is quite important. We need to, develop more, digital functions to monitor, in detail of the tracker or any small pieces of equipment in this system. We need to make the whole PV system stable, and then to increase the PV production by using like Trina Tracker's smart tracking algorithm, and that's what I want to say.
Okay, wonderful. Thanks a lot to everyone. Maybe just a few words to conclude from my side. So I think Miguel mentioned actually one important event also. Of course, first, thanks to Trina Tracker for sponsoring this webinar. Miguel mentioned actually the Solar Quality Summit, which will be organized end of January in Spain. That's basically when the solar power plant community is meeting. This is organized by Intersolar and Solar Power Europe. And I think that's really worth going, because many of the topics that we already also discussed today will be there discussed in more in-depth. I would also like to point at the next webinar that we are organizing. Here are a couple of reports from Taiyang News you can download. And then the next event will take place in a week. And there we will look into back contact PV module technology for rooftop applications. Thanks again for everyone. Sorry again for the little glitch in the beginning, but that's also digitalization. And as we learned, we are just at the beginning. Everyone, have a nice evening, have a nice day, and talk to you soon. Bye-bye.